Hello, we are continuing with pulse modulation. In today's class, we will discuss these topics: pulse code modulation system, block diagram, uniform quantization, quantization error, quantization noise power, signal to quantization noise ratio, companding, mu law for companding, A law for companding, line coding techniques, unipolar signaling, unipolar non-return to zero signaling, unipolar return to zero signaling, polar signaling and polar return to zero signaling. Now pulse code modulation is a modulation technique. This is a digital modulation technique in which the pulses are, that means we already have gone through pulse amplitude modulation, pulse width modulation and the pulse position modulation, which are all analog modulation technique, because in those cases the number of that is amount of amplitude of the pulse which is proportional to the message magnitude, that means instantaneous magnitude of the message. Similarly, width of the pulse or position of the pulse was varied according to the instantaneous magnitude of the message signal. So that is why that was the analog kind of modulation technique. But here the pulse code modulation means the pulse magnitudes are again converted into binary codes, and those codes will be transmitted, not the magnitude variation, not the width variation, not the position variation. That is why pulse code modulation is nothing but a transmission of fixed amount of symbols which are having fixed magnitude. The magnitude is not from a infinite set of magnitudes. So that is why, as the magnitudes are fixed, which are taken from fixed set of value, that is why it is known as the digital communication. So in case of pulse code modulation system, the analog signal is first converted into sampled signal, thereafter it is quantized and finally it is encoded. So sampling process, we already have seen that by the process of sampling, a signal which is continuous in time and amplitude is converted to a discrete in time but continuous in amplitude signal. For sampling, the sampling theorem has to be followed. That means the message frequency must be limited to a high message frequency component, otherwise it is required to be low pass filtered, which is known as the pre-aliased low pass filter, so that the message frequency will be limited to a highest value, so that sampling theorem could be applied. And thereafter those sampled knowledge of the message signal is quantized. Quantized means the message magnitudes which are taken from infinite set of values will be approximated, so that the fixed set of magnitude of the pulse height may be approximated, which is known as the quantization process. So quantization is nothing but mapping the pulse magnitude with the predefined table values, so that the magnitude will be approximated to the fixed set of values. So this is known as quantization process. So this quantized signal is further encoded into binary bits. So how it is done? Because the quantized magnitude are nothing but the pulse magnitude, as the pulse magnitudes are converted into fixed set of values by the quantization process, therefore quantized signal is itself a digital signal, because it has finite set of magnitude values only, and these finite set of magnitude are further encoded by binary encoding, in which either 2-bit, 3-bit or 8-bit may be imposed for encoding each of the pulse magnitudes. We know for n number of binary bit there are 2 to the power n number of possibility. So therefore we have to see that how many number of quantized magnitude is possible by quantization process. So if it is m, so m should be lesser or equal to 2 to the power n. In this way, n will be the required number of binary bit to encode each of the quantized magnitudes. Now this is the overall block diagram for the pulse code modulation system, in which initially the continuous analog signal is applied to the input of the pulse code modulator circuit. Here bandpass filter is required because it will limit the higher frequency component of the incoming message signal to a fixed quantity, so that message will be band limited, and band limited message signal will be further applied to the sample and hold circuit so that the sampled uh, message signal could be obtained, which is known as the pulse amplitude modulated signal. So pulse amplitude modulated signal, up to this it is an analog signal, and this analog signal is need to be converted into digital pattern by means of analog to digital converter. So analog to digital converter does two things. One is the quantization and further is the encoding. So therefore, uh, finally AD converter produces the binary bit where the number of binary bit are parallelly processed to the parallel to serial converter, where all these parallel binary bits are made inline. That means only one communication channel is utilized for transmission of the serial data. So serial PCM data bits are transmitted and it is received by the regenerative repeater. Now what is repeater? Repeater is a device which is required to boost up the transmitted signal when it is deteriorates due to the transmission path. That is, if the transmission path is longer, then the signal is required to be boosted up. That means the magnitude of the binary bits, if reduced to a lower value, then it is required to be amplified and regenerated. That means the whatever is the bit pattern transmitted earlier, the same thing should be re-established by means of regenerative repeater because of the degradation of the binary bit when it is traveling through the communication channel. So such regenerative repeater stages will be multiple if the amount of distance between the transmitter to receiver is very large. Finally, it is reaching the receiver where the first stage is the serial to parallel converter that converts the serial data bits into parallel line, and these parallel binary bits are applied to the digital to analog converter so that the equivalent analog signal is obtained, which is nothing but the pulse amplitude modulated signal, which is passed through a hold circuit and applied to a low pass reconstruction filter to produce the message variation. That means the slope of the message will be re-established by means of the low pass reconstruction filter processing. Now this is the quantization process. There are two types of quantization process. One is the mid-rise type, another is mid-treat type. Now the definition is very much straightforward because the mid-rise type is showing that both are staircase waveform, and the mid-rise type is showing that at the 0th position of the input, the rise of the stair is occurring. So that is why it is mid-rise type. But if at the 0th position it is treat type, that means it is horizontal, then it is the mid-treat type. So these are the two type of uniform quantization which is occurring. And why it is uniform? Because the height of the corresponding staircase waveform is fixed. It is not varying. Here it is taken 3 delta by 2 minus delta by 2, that means it is delta only. So delta is the height of the staircases, that is smallest height, that is known as the step size of the quantized waveform. This is known as quantization error. As we know, the staircase waveform is known as the quantized signal. Now for a particular slope of the message, as we see V in versus V out, this is a simple line is taken, but the quantized waveform is a staircase waveform. So every time either the staircase waveform is exceeding the value of the analog signal, or sometimes it is going down with respect to the analog signal. So therefore, every time there is a possibility of existence of quantization error, that is a difference between the message signal and the steps, that means height of the step or the horizontal part of the step. So therefore, this error will exist, but we need this error to be minimized. Now, for the calculation of the quantization noise power, first of all, you have to see what is the probability density function of quantization noise, and thereafter multiply it by the random variable, square of the random variable, and if we integrate, then we are getting the quantization noise power, and it is given by del square by 12, where delta is the quantization steps or step size. Now here it is showing that if the message signal is having some lower limit to upper limit, then the message signal may be represented in terms of the binary bit. In is the binary bit and delta is the step size. So therefore the maximum signal RMS value is given by the equation which is shown above, and the bottom is the maximum signal to noise ratio, where the 20 log the ratio of the output voltage to the input voltage. That means the signal power by noise power is taken, and here the 20 log square root 6 by 2 to the power n. So finally we are getting the equation of the signal to noise ratio for the pulse code modulated signal. Now next is companding. Companding can be divided into two words. One is called compression, another is expansion. So why this companding is required? Sometimes the message magnitude has a great fluctuation. Therefore, whenever we are going to encode such a sample, or whenever we are going to quantize or sample such a signal, then there is a great amount of error. That is why the magnitude fluctuation may be minimized by compressing the message signal by means of two number of laws which are known as mu law and A law. Otherwise, what will happen? The quantization and encoder will have a huge amount of error that may not be compensated when the signal is recovered at the receiving end. So this is the mu law. The mathematical expression is given where Vmax is the maximum uncompressed analog input amplitude, and Vin is the amplitude of the input signal at a particular instant of time, and mu is the parameter used to define the amount of compression which has no unit. Therefore, output voltage is nothing but the compressed output which we are getting, which is possible to be quantized as well as encode. Similarly, A law is having some other mathematical expression, but the target is to find same. That is, we need to reduce the quantization error so that the error of recovery of the signal at the demodulator will be less. Now, line coding is one of the important part of the technique for the representation of the signal. That means pulse code modulated signal, as we already have told, that it is nothing but the sequence of binary bits. But how these bits could be represented? If it is a simple 5 volt and 0 volt, there are a lot of chances for which it will be facing error when it is propagating through the channel. So how to protect this bit? How to make this bit robust when they are propagating through the channel? How to provide some synchronization information within this bit? How to provide some noise immunity to this bit? And if there is a transition, that means if there is a continuous fixed amount of voltage and thereafter there is a transition, then whether the magnitude will be defeated below the threshold or not. So there are so many queries regarding the transmission of binary bits. So such query may be solved. That means such errors may be reduced by means of a technique known as the line coding technique. This is nothing but the representation of binary bits by introducing special shape of the electrical magnitudes. So a line code is the code used for data transmission of a digital signal over a transmission line. This process of coding is chosen so as to avoid overlap and distortion of signals such as inter-symbol interference. So inter-symbol interference is one of the error which is occurring in case of digital communication transmission, where the symbols adjacent to it will overlap with the other one, and the actual magnitude information of the symbol is lost. So such an error is known as inter-symbol interference. The properties of line coding are very much important, as the coding is done to make more bits transmit on a single channel, on a single signal. The bandwidth is used is very much reduced. For a given bandwidth, the power is efficiently used. The probability of error is much reduced. Error detection is done, and the bipolar 2 has a correction capability. Power density is much favorable. The timing content is adequate. Long string for ones and zeros are avoided to maintain the transparency. So this is known as DC wandering, which is occurring for long transmission of ones or zeros. The types of line coding are three types. There is unipolar, polar, and bipolar techniques. Now, what is unipolar signaling? For the unipolar signaling, only one type of magnitude, either positive or negative magnitude, is taken uh, in unipolar signaling. Unipolar signaling is also called on-off king or simply OOK. So it is the amplitude which is varying, that means either positive magnitude or negative magnitude, but both cannot be present. That means only single polarity is allowed. The presence of pulse represents logic 1 and the absence of pulse is logic 0. There are two variations of unipolar signaling. One is the non-return to zero, another is return to zero. Now here non-return to zero signaling has been described. Now clock is nothing but it is an oscillatory rectangular pulse which is having positive magnitude as well as negative magnitude within a bit duration. So bit duration is equal to clock duration. For the data bit, it is having 1 or 0 sequence. For the unipolar not return to 0 signaling, we are getting that the representation of 1 is the presence of pulse and representation of 0 is the absence of pulse. The advantages of unipolar not return to 0 is the circuit is very simple and it is utilizing less amount of bandwidth, whereas the disadvantages are it has no error correction uh, possible, that means error may be introduced easily. Presence of low frequency component may cause the signal drop. No clock pulse is present. Loss of synchronization is likely to occur when there is a long string of ones or zeros. Unipolar return to zero signaling is shown here. The difference between between the not return to zero and return to zero is that within the pulse, positive pulse, that means for logic 1, we already have seen positive pulse is utilized for not return to zero. So for the positive pulse for uh, return to zero is having a transition at the middle of the bit interval. So therefore, as there is a transition of clock is observed at the middle of the bit interval, at the same position there is a transition exists for unipolar return to zero. But for the logic 0 there is no pulse because it is unipolar, that is why there is no pulse for logic 0. Now unipolar return to 0 is having some advantage. It is again a simple circuit. It is the spectral line present at the symbol rate can be used as a clock. The disadvantages are it has no error correction, uh, occupies twice the bandwidth as unipolar not return to zero. The signal drop is caused at the place of signal where non-zero at 0 Hz. Now thereafter there is a polar signaling. Polar signaling means positive as well as negative height of the voltage is possible. So for data bit 1, it is a excursion between the negative voltage to positive voltage. Uh, that means minus V is the lower voltage and plus V is the higher voltage. So logic 1 it is a positive pulse and for the logic 0 it is a negative pulse. So now as the voltage excursion has been increased in case of polar signaling, therefore the noise immunity of such signaling is much high compared to the uh, unipolar signaling, because the pulses are traveling in the communication channel are gradually deteriorate its magnitude due to the superposition of the noise in the channel. So that is why if the voltage excursion has been increased by polar signaling, then the degradation of the pulse will be little bit less compared to the unipolar signaling. So therefore it is more immune to noise. And what is polar signaling? The advantages of the polar signaling are it is simple and it has no low frequency component. But disadvantages are it has no error correction, no clock is present, it has no clock. The the signal drop is caused at the places where the signal is non-zero at 0 hertz. Now the polar return to zero signaling is also known as the alternate mark inversion, that is AMI coding, in which successive ones are represented by half bit positive, half bit duration positive pulse, and next half no pulse. But for zero, it is the negative half bit duration pulse, and the remaining part has no pulse. So therefore, for the polar return to zero, we are observing that logic 1 and logic 0 are represented by half bit duration pulse, but for logic 1 it is a positive, and for logic 0 it is a negative pulse. So such a polar return to zero signaling is having advantages that at the middle of the bit interval there is a transition, therefore the clock recovery from such a message is possible. So we don't need a separate clock at the receiving section because the transmitted signal is having transition at the half of the bit duration, which is the clocking instant. Therefore, the message is sufficient to extract the clock information from the for the receiver. And there are some disadvantages. The circuit is complex and the processing requires some expensive circuits.